Hi everyone, I'm Philipp Terst from Fraunhofer IGD in Darmstadt, Germany, and this is our work SER-FIQ Unsupervised Estimation of Face Image Quality based on Stochastic Embedding Robustness. Face recognition systems are spreading worldwide and are increasingly involved in critical decision-making processes such as in forensic investigations or border control due to their high recognition performance. The task of face verification aims to verify a person's claimed identity. For example, if I claim I am Philip, my image is captured and the system aims to answer the question, is this Philip? Therefore, in the pre-processing step, the image is aligned, cropped, scaled, and so on to ensure that the image is suitable as an input for the face recognition network. And this network produces a high-dimensional feature representation called template representing my identity. The face recognition network is trained to minimize intra-identity variations and to maximize inter-identity variations, meaning the representation of the same person should lie close together, while the representations of different persons should be far away from each other. With the template of my captured image, we can then search in the database for the stored template of the claimed identity. And comparing these templates with a similarity function, for example, cosine similarity, results in a comparison score. And if this score is above or below a certain threshold, the system comes to the decision that it's a genuine or imposter comparison, meaning a match or no match. Under controlled conditions, current face recognition systems perform highly accurate. However, under unconstrained environments, these systems have to encounter large variabilities, such as illumination, blurriness, or resolution, or occlusion, different poses, expressions, or if the system simply encounters a sample that was, for example, not well represented in the training data. In these cases, the recognition performance might be strongly degraded. In general, the performance of biometric recognition is driven by the quality of its samples, and the biometric sample quality is defined as the utility of a sample for recognition. So if you have a face image that is frontal, not covered, well illuminated, the utility is generally higher than if you have a face image that is more or less occluded with hair and, for example, with a mask. Recent works proposed solely supervised solutions for the task of face image quality assessment. These are based on human labels or on artificial labels. So the artificial labels are based on comparison scores. However, these are typically biased if low quality samples are used for creating these artificial quality labels. On the other side, human labels, they transfer human bias into the face quality assessment systems. And also humans may not know the best characteristics for an automated face recognition system. Avoiding the use of inaccurate quality labels, we propose a novel concept of measuring face image quality using the robustness of a representation as its quality indicator. And here, the robustness refers to the robustness against dropout variations. If you have an input image I, the idea is to randomly eliminate nodes from the deployed face recognition network and use this reduced network to produce a stochastic embedding. And this step is repeated 100 times, resulting in 100 stochastic embeddings. And the variations between these embeddings can be used to determine the robustness of the representation and thus to determine the quality of the image. So why does it work? As we saw before, face recognition training aims at being robust against intra-identity variations, and an image that produces relatively stable identity-related embeddings despite various variations is an image with high utilization in a recognition task. So let's take a closer look at this. We have an input image I that is put into the face recognition network consisting of convolutional layers, pooling layers, and the two last layers are fully connected, and the output is a face embedding of I. Now the idea of SER-FIQ is that we render nodes from the second last layer via dropout, for example, and this gives us a stochastic embedding using this sub-network here. And then we will simply repeat this process. So we randomly eliminate different nodes, resulting in a different stochastic embedding. And this we repeat again, randomly eliminating nodes, new stochastic embedding, and again. This we will do 100 times, so here we'll just do it for 4 times. And the idea is now that we compute all pairwise distances between the different stochastic embeddings. And with this pairwise distances, we can compute the stochastic variations between the stochastic embeddings, which is simply the mean pairwise distance between all stochastic embeddings. And if we have low variations in these stochastic embeddings, this refers to a high robustness and therefore to a high quality of the phase image. On the other hand, if the variations are very high between the stochastic embeddings, the robustness is low and therefore also the quality is considered as low. This part here refers to the embedding robustness, and 2 times the sigma function is just there to bring it into a range of 0 to 1. For the experimental setup, we evaluated everything in a cross-database evaluation setting on 3 public available databases. The evaluation was on 2 popular phase embeddings, PhaseNet and ArcPhase. These losses were used. And we compared against 6 state-of-the-art approaches from academia and industry, 3 for general image quality and 3 for phase image quality. We have also 1 industry product here from Neurotechnology, then an approach from Best Roden and Anil Jain, and PhaseQNet. And we report 2 variations of our method. One is the on-top model, where we trained a small recognition network with a dropout on top of the deployed one. The more interesting one is the same model approach. There we just used the deployed face recognition model without any training to predict the quality, just by applying this SER-FIQ concept on the network itself. So we evaluate the face image quality assessment performance with error versus reject curves, since there is no clear definition of quality we could compare to. The general idea is to increasingly reject low quality samples, and on the remaining higher quality samples, the error should decrease. On the y-axis, you see the face recognition error, here in terms of false non-match rate at a false match rate of 10 to the power of -3, as recommended by the European Border Guard Agency. On the x-axis, you see the ratio of unconsidered images. For example, at 20% ratio of unconsidered images, 20% of the lowest quality images are removed from the dataset, and the face recognition error is computed on the remaining higher quality images. Consequently, with an increasing ratio of unconsidered images, the errors should steadily decrease. And you see the results on the ADIANS and LFW databases based on PhaseNet embeddings. And if we take a look how the general image quality assessment approaches work, this is here. They have nothing to do with face recognition, it's just the image quality itself. You see that on ADIANS it shows no effect at all, on LFW it shows a little effect, but in general, face image quality is not so much about image quality itself. This is the approach from Best Roden, especially on LFW, it works quite well. This is for PhaseQNet, which works well on ADIANS, and at the beginning on LFW, at the end it has some problem with determining the quality correctly. This is from the industry product, so it works quite steadily and well. And this is our approach, SER-FIQ, especially the red one is the training-free approach, where we just throw the concept on the face recognition model, and most of the times it outperforms the baselines. Here you can see the results for the ArcPhase embedding. So we use a network that was trained with ArcPhase. These are the performance for the general image quality approaches, and you see, okay, image quality itself has more or less no effect. This is for Best Roden, it works steadily. This is for FaceQNet, which also works quite steadily. Just at the beginning on LFW, there's no change. This is for the industry product. So in Adience, it works well. On LFW, it shows more or less no effect. And this is our SER-FIQ approach. Again, a red one is the training-free one, where we just apply the method on the face recognition network, and it works quite well. You can see some sample images with the quality values from face image quality assessment approaches. Our SER-FIQ approach here refers to the quality values based on the ArcFace model, and all quality values are normalized to a range of 0 to 1, such that they are comparable to each other. And what you can see is for the first two images and the last image that the quality is very low from the SER-FIQ method, which refers to that young people don't have the identity information developed, therefore it's hard to distinguish between them. And also the first image, you see it's a little bit blurry and the head pose is non-frontal, while in the middle you see faces with much higher face image quality values, since they are frontal, taken frontally, and the image quality is high, it's well illuminated. But you can also see that if the pose changes from frontal to non-frontal, the quality drops. To conclude, the performance of current face recognition systems is driven by the quality of its samples, and the quality is defined over the utility of a sample for recognition. In this work, we proposed SER-FIQ, a novel concept of measuring quality, face image quality, and it defines the quality over the robustness of the representation against variations. The advantages of this approach is, for example, that it's applicable to arbitrary face recognition networks, and in contrast to previous works, it's training-free, parallelizable, and highly effective. With this, thank you very much for your attention. If you're interested, code, papers, and further information are also available on our GitHub page.